Hey everybody, good morning. Hope you all had a good long weekend. All right. So we left off last class talking about scatter plots of the relationship between two continuous variables. So last class we talked a lot about how to summarize that information in terms of like the strength of that relationship, its shape, and so on. Okay. And then this time we're talking about the introduction to regression. Okay, so here's our learning objectives for today. So you can take a quick second to look at what those are. Some of this should be a review for many of you, the concepts of linear regression and how to fit a line of best fit. But if it's not, what I recommend is that you come to office hours this week and just go over some of these concepts about regression that we're kind of assuming that you already know about. Okay. So picture that scatter plot or something that we made on last class. And imagine you have the X and Y variable and you have this cloud of points. And this cloud of points, there's a relationship, a linear relationship between these two variables. So you have a cloud of points around like a line. So that line we call the line of best fit. And the way that it's chosen, its position in that cloud, is chosen using what's called least squares regression. Least squares regression is also called ordinary least squares or OLS. So whenever you go on after this class and you're reading papers, they might say they're using any of these forms of regression, or they might just call it linear regression. And it's assumed that they're using this mechanism to fit the line of best fit to the data. We're not going to talk too much about the mechanics here about how the line is fit to the data, like the actual algorithm that's used to fit that line in terms of its position in the cloud of points and its slope. But what least squares is saying is that there's a squared distance between each point and the line. So here's a point, each point and the line. And you want to minimize the area. And that's kind of how it's done. Okay, so some of the key terminologies that we talked about here is that the data, the line is fitted to the data. It's called the line of best fit. And then you know what these terms are for that least squares OLS. Okay, so when we fit a line to data, we have R do it for us. So we run a function. The function's actually called LM for linear model. And R will fit the line for us. So before we do that, one thing you need to do that R won't tell you to do is visualize the relationship between X and Y. So use our skills from last class when we made that scatter plot to look at the relationship between X and Y and make sure that its shape is linear. Because what will happen is, suppose that you had a non-linear shape, a non-linear relationship between the data, the line of best fit will still be fit to that shape, but it won't actually be a really good summary of the relationship between the data. So the key takeaway, before you fit a linear model, you should always plot your data and ensure that the shape is approximately linear. Okay. Because if you don't do that, R will just run the model and tell you some linear, summary, and that summary won't really be capturing what's truly happening to the data. Okay, so this is where I was saying this should be a bit of a review. Maybe the notation is different, but if it's not, please go to office hours this week and chat with your GSIs about what we're showing you here. So the equation for the line of best fit should look like this. So here in the textbook, it's represented by y equals a plus bx. When I learned about this, it was y equals mx plus b. So you might have used different symbols or letters to stand in for these different coefficients than what's shown here. And one thing this just reminded me of, I set the textbook, and if you go to the course website and hit textbook, it now has a link to the first 3 chapters. Or no, it's chapters 3 through chapter 6. And right now I think we're on chapter 4. So we have some of the chapters digitized. They're giving us access to the rest, and hopefully by the time we get to chapter 6, we'll have all of them available for you. Okay, so in the way this is written, we have an intercept and a slope, and those coefficients is what's being estimated by the model. So we're estimating the best value of the intercept term A and of the slope term, which is represented by B here. Okay, so let's go through and chat about what A and B stand for. Okay, so the intercept is represented by A, and what it says is if X is 0, then it's the value that Y takes when X is 0. So again, we have two variables, an X variable and a Y variable, and we're trying to summarize the relationship between X and Y. And so we can say, what's the value of Y when X is equal to 0? So you can picture your like data frame with all your data. And if you had a positive relationship between X and Y, you have this shape, and then you could say once X is equal to 0, what is the value of Y? And so sometimes the value of the intercept is meaningful, and other times it is not. And when it's meaningful is when X can like really take the value 0. Sometimes with certain ranges of data, it doesn't make sense for X to ever be 0. So we'll talk about one of those examples today, so you can get an example of that. Okay, so we talked about the A, which is the intercept, but what about B, the slope? So the slope term is really this whole rise over run, right? So it's like if you change the value of X by 1 unit, then Y changes by the amount represented or estimated by B. So it really tells you how much Y changes in response to X changing by 1 unit. There's a relationship between the slope B and the correlation coefficient R. So last class, we talked about the correlation coefficient as a way to summarize the strength of the relationship between X and Y. So remember that this correlation coefficient R goes between -1 and 1. If you had a number really close to -1, it's a strong negative relationship. And if you had a number closer to +1, it's a strong positive relationship. And an R close to 0 is a really weak relationship or no relationship. So the relationship between the slope and the correlation coefficient is this, where S sub Y represents the standard deviation of the Y variable, and S sub X is the standard deviation of the X variable. And I just added these two sentences to my version of the slides. So you might want to jot them in your notes if you don't have them, because they're not, these descriptions of S sub Y and X aren't in your version of the slides. Okay. So we talked about the slope and R, the correlation coefficient, but sometimes we square the R value. We take R squared, and it's called the R squared value. And when you do that, it actually presents another piece of information which is useful. So what R squared tells you is the fraction of the variation in the values of Y that is explained by the relationship between X and Y. So it's a fraction. So this R squared, again, will vary between 0 and 100. And it will, I guess 0 and 1. By the way it's presented. So like you'll have an R squared value of say 0.43. And so that will say that 43% of the variation in Y is explained by changes in X. It might seem weird or redundant to have both R and R squared. And it is when we have what's called simple linear regression, which is the framework we're working in right now. So simple linear regression is when you only have one Y variable and one X variable. So you're just looking at the relationship between one X and one Y, that simple scatter plot. Later on in your next stats course, you'll learn about multiple linear regression. And that's when you put numerous X variables in the model. And when you do that, you're still trying to explain variation in Y, but not just based on one predictor of Y, one X, or one risk factor for Y. You're putting a lot of things in the model to predict Y. And when you do that, you get an R squared value for the entire model. So R squared is for the entire model, and it again encapsulates what percent of the variation in Y is explained by all of the X's together in that setting. So in that setting, you'd have 1R squared for the model, but these R's, these correlations, are only between each X and Y. So say you had 5 X's in the model, you might have like age, weight, all these other things about a person. If you were, and then what you could do is make a scatter plot for each X against Y and calculate the correlation between X and Y. And then separately, the next step, you put all the X's in a model and you calculate the R squared for the model as this measure of fit. So the higher the R squared, the closer it is to 1, the better the X's are able to like fit the data and tell you what's happening in Y. Okay, I'm gonna look at the check quickly. Okay. So how do we do this in R? So I told you already that the function is called LM. So to use the LM function, you don't need to load a library. It's very standard, so it comes loaded already. So no library to use LM. The first thing you pass the LM function is what's called a formula. And the formula is just, as it's shown here, Y tilde X, where Y and X are the variables you're modeling. So Y is the response variable and X is the independent variable or the explanatory variable. So again, in some settings, we talked about this last class, it's clear what Y should be. In some settings, remember that one with the rain and the bushels of corn? So there was like a daily amount of rain. That was your X variable. And we're trying to use that to predict the bushels of corn yield from an area of land. In public health, Y is often like some sort of health outcome or measure of health, like blood pressure or something like that. And X could be some exposure. So something about diet or policy or all of these sorts of things that people are exposed to their lifetimes that affect, or we think that they affect their health. Okay, so we pass it the names of those variables, and then you go comma and you put in the name of your data frame. Okay. Good. So we got all of that. One thing I do want to point out is this order, Y tilde X, is the opposite of what we're used to from ggplot. So in ggplot, we did data first, comma, AES, X, then Y. But here we're doing Y tilde X, comma, your data frame. So it's all kind of flipped around. So just keep that in mind, because that's a place where you can like kind of trip up on a test or something if you're writing this code and you get the order wrong. So just kind of keep track of these little differences. Okay, good. All right, so that's when you run your linear model. What you're going to do is like the same sort of format we did before. We're assigning it to an object. So we run the model and we store that model in whatever you want to call that. So you could call it, I like to use like an underscore LM to remind myself what I'm storing. So here I'm storing a linear model. Whereas like if this was like a ggplot command, then I might do something underscore plot. And then you always like have some sense of like, oh, what's stored in that variable? Because if you just called this like, suppose like we were modeling something to do with the air quality and asthma, maybe hospitalizations or like asthma attacks or asthma medications. If you were running that model, before you ran the model, you'd make a plot of the AQI and these asthma outcomes. And then you'd store that plot and you could call it, if you just called that plot asthma, and then later on you went to run your linear model and then you called that, I don't know, asthma 2 or something like that. When you go back later and see these things sitting in the R environment, it doesn't like telling you what those things are. So this is to be friendly to yourself. You want to name it something like a noun, so you know what's stored in there. So this is just good practice to like try and put like, oh, this is an LM here. And we did that also with the data sets, right? Sometimes we called it something underscore dat for that same reason. All right, so we do end up loading this library, this other library called Broom. And that Broom library, oh, my lights are going off. Okay, my Broom library gives us access to the function called tidy. So tidy is a function that allows you to nicely look at the results from a linear model. And it presents the results in this little table that's kind of the format we're already used to. It actually presents the results in a little data frame. So Broom, again, is a library to give us access to the function tidy. Okay. I'm going to take a quick look at the chat. Okay. So, oops. Okay. Let's go here. So you guys commented that my examples were depressing, and they were from last class, but we're back. We're back to the depressing example. So again, let me remind you, we were looking at manatee deaths, and those deaths being a function of this explanatory variable, the number of powerboat purchases. These data are from the textbook, so you can actually go and look at that data set on page 70 of the textbook from the course website if you want to do that now, just to get, it presents a little more background information about that example. So remember that we made the scatter plot and it looked like this between powerboats and deaths. Deaths is the response variable, powerboats is the explanatory variable. Okay, so when we're running the model, right, what we do is we write LM, deaths are Y variable, tilde X are powerboats. So these are the names of those variables in the data set, comma, this was called mana data. And so we had already read in the data to R at this point. And then we assign that to mana LM. Okay, once we do that, you don't get any output yet. You could if you just looked at this by itself, but if you do that, if you print mana LM to the screen, it'll be a little bit messy. So to look at it, what we do is we load the Broom library, and then we write tidy LM. And when we do that, we get this little rectangle of output. And what I want you to pay attention to now is just this estimate column. Don't worry about standard error, stat, or p-value. We'll talk about that towards the end of the course. So just the estimate for now. What the estimate corresponds to is the coefficient estimates for A and B. So A was the intercept, and B is what's shown here across from powerboats. The reason this says powerboats rather than slope is because remember I told you we're in the framework of simple linear regression, where you only have one X variable. You could actually, rather than just having powerboats, you could have several explanatory variables. So for the manatee death data, right now, these deaths, they're thinking are a function of powerboats. But what else? Go to the chat and tell me what else might manatee deaths be a function of. So these are manatees living in the ocean. What else could explain maybe a rising death rate? Yeah, so things having to do, I'm seeing all of your answers roll in about pollution, plastic, ocean temperature, ocean acidification, oil spill, exactly. There's a lot of things there that could explain, like if you saw this rise in deaths, say you didn't know anything about the power boats being, more of them being purchased over time, you might look into these other explanatory factors. And indeed, in like other areas and in other, not just manatees, right? Other creatures in the ocean are being like, you know, dying because of climate change. Okay, so let's interpret these estimates for a second. So the intercept term, right? This is a negative number. So this is saying when X, the number of powerboats registered is 0, the number of deaths is -46, which seems odd, right? So let's decide whether we should interpret that and think about why we might not want to. Okay, and powerboats is the slope term, but one thing that I didn't make clear in the slides is that, let me just see here, is that in the original example, if you go look at the data, then the powerboat registrations is actually in thousands. So this 447 represents 447,000. So there's like 3 zeros that need to be added to each of these X variables. So you could have mutated the data to have like a powerboats 2, right? That actually performs that. So you actually have the variable in its actual unit. So keep that in mind because that affects our interpretation. So the reason our interpretation will be different is because the number of powerboats registered is multiplied by 1,000. Okay, so if we go to that estimate of the slope, this is saying for every 1 unit change in the number of powerboats registered, so 1 unit would be going from like 447 for 448, but actually it means from going to, let me just like write this down. So 447, and then in thousands, yeah, so it's 447,000 to 448,000. The number of deaths go up by 0.136. Okay, that is hard to interpret when you have a number of deaths going up by a decimal place. So when that happens, it's easier in terms of like interpretation to do something like what's on the next slide. Okay, so just look at this first. So this is our baseline interpretation of the slope, which is correct, but hard to interpret. A 1 unit change in the number of powerboats registered multiplied by 1,000 is associated with an increase of manatee deaths of 0.1358. And you can say that in a different way. 1,000 unit increase, right? And that's because of this multiplied by 1,000 thing. And the number of powerboats registered is associated with 0.1358 more manatee deaths. Okay, so then what does that mean if powerboat registration increased not by 1,000, but by 100,000? In that case, how many more manatee deaths are there expected? Right, so I'm seeing some of you writing the answer in the chat. So how folks got this answer, so people are writing 13.58, and what they're doing is they're taking the slope estimate of 0.1358, and they're multiplying it by 1,000. Yeah, wait. Is that the right, are we moving that decimal place over enough? Or should it be 1 more unit? Multiplied by 100. Why 100 and 1,000? I am confusing myself. I think it's 135.8. Yeah, I think that's, yes. I think that's what we should be doing, right? Right, because the zeros, okay. Oh no, it's 100,000. Oh, I've confused myself. Okay, and I confused some of you as well when I said that. Okay, so the original estimate was multiplied by 1,000, and now we have 100,000, and that's 100 times larger. So we move the decimal place by 2. So sorry for the confusion, but yes, the 13.58 is the right answer. Got it. Thank you all in the chat for clarifying that. Beautiful. All right, good. So just pay attention when you get a question. If there's any setup like that, then you have to do a little bit of this mental math. And sometimes, like me, you'll get it wrong. Okay, so, all right. So what we can actually do is add the line of best fit to the data. And so we can go back to our original scatter plot and use geom_AB line to add the line of best fit to the data. So here's what we do is we make our scatter plot between X and Y. We use geom point to make the scatter, right? We add our labels, and then geom AB line takes two arguments, the intercept and the slope. So you pass it from the linear model, the estimate of the intercept and the estimate of the slope. And so that is how we got this line. So this is the line of best fit to describe this data. So a 1 unit change, so going from 600 to 601, will lead to more manatee deaths of 0.1358. But again, remember, this times 1,000 thing. So just pay attention to that when you're doing your interpretation. All right, good. So remember when we had the intercept and the intercept was negative, so it seemed like when powerboats registered was 0, it was predicting that there'd be a negative number of deaths, and we thought that was really unusual and also couldn't happen. So why was that? Why did it give us this negative estimate? What happens is, this is the range of the data. The data, the X number of powerboats registered, the lower bound is actually around, it's just under this 500. But if you extend this out to what the line of best fit says, when X is 0, it's a negative number. So it's predicting, it's extending or extrapolating this line of best fit beyond the range of the data, way outside of the range of the data, to say, oh, well, according to this line, when the number of powerboats registered is 0, manatee deaths are negative. And the reason that failed is because this is extrapolation. So we have no data out here, and we're using the line to summarize what would happen had number of powerboats registered been 0. But that estimate is not informed by data in this range. Because what would actually happen is, if the number of powerboats registered kept getting lower and lower, the number of manatee deaths cannot go below 0. So you'd actually get one of these like J shapes in the data rather than extending this linear line. So the key message here is that you don't want to be interpreting an intercept if it's really outside of the range of the data, because this data that exists between like 450 and 1,000 won't do a good job informing us what would happen if X gets to 0. And so that's how that, misinterpretation happens. So here is an example of where we can't interpret the intercept just because it's because of extrapolation. We get into trouble. Okay, so one other new function for the day is called glance. Glance also comes from the Broom package. And so you want to glance the linear model. So you're passing glance the linear model, and you're using that to look at the first column of glance, which is the R squared. So the R squared value here is 0.893. So this is saying that 89.3% of the variation in the number of manatee deaths is explained by powerboat registrations. Okay, so that's really high. In public health, especially if you just had one variable, it's very rare that you would see something so high. Even if you're building a prediction model, so you're trying to do your very best to predict some health outcome, and you're throwing in all of these risk factors or predictors into the model, you might only get an R squared of like 0.4 or 0.6. And so it's often really hard to get an R squared value that's so high in public health. But in these kind of toy examples from the book, they happen. So one example I gave where you might see like a strong relationship was with, if you looked at as your X variable, the percent of the population who's vaccinated against HPV, and that has increased really prominently over time, right, since the vaccine was introduced, and also with your Y outcome as the incidence of new cases of cervical cancer, those things will be really inherently tied. And that's because 91% of cervical cancer is estimated to be caused by, and truly caused here, not associated with HPV. And so if you are able to prevent HPV from ever occurring, you can prevent these incidences of cervical cancer. It's not often we have like these sorts of relationships where it's so tied like this, but I just wanted to give you an example of the sorts of situations that give rise to these high R squared, but oftentimes the R squared values are lower. Okay, and quickly look at the chat. Oh, that's an interesting question. There's a question in the chat that said, so for our example on HPV and cervical cancer, I told you that 91% of cases of cervical cancer are due to HPV. And somebody asked, would that mean that the R squared of that value would be 0.91? It sounds like it should. I'm trying to think off the top of my head if there's a reason that we would expect it to deviate more than that. There probably is that I'm not thinking of off the top of my head. Let me keep thinking about that, and I'll report back later if I can come up with a better answer to that. Okay. A good R in the real world, I think it really depends on, or a good R squared, your circumstance, like what it is that you're modeling. So there's certain sort of outcomes where that are more easy to predict than others. Like I'm just thinking like one thing that's really hard to predict is the risk of preterm birth. And we know all of these risk factors for preterm birth, but it's hard to predict. So that R squared value for that model where risk of preterm birth or outcome would be probably lower than for some other health outcome that we could explain better. Yeah, it really depends. I think what you want to keep in mind if you're a modeler doing this sort of thing is you're just trying to do a better job than what is already known in the literature. So maybe in the literature, somebody built a model and they were able to explain, 42% of the variation. And then you built another model, you have electronic health records or something, and you have all of this data measured over time of different people, say, and you're able to explain 64%. So 64% compared to 42. So you can make a better prediction than someone else. We're not going to get more into that, like how to actually tell whose prediction is the best, because there's other mechanisms to do that. But that's kind of the next course in statistics, how to build a prediction model and look at that. Okay, good. So let's move on to the next example. So the next example is also from the textbook. And what it's looking at is these different species of trees and the relationship between the number of seeds, like the count of seeds, and the weight of those seeds. So when you look at that, if you plot it first, so we have seed count and seed weight, and we're putting seed weight on the Y. I feel like this one to me is less clear if I was to say, oh, is there a clear, response and explanatory variable? Maybe if I knew more about trees there would be, but anyway, we're putting seed weight on the y-axis and seed count on the x-axis. And what you're ending up with, like, do you want to run a linear model on these data? What do you think? Should we? No. Yeah. Yes, we do not. Yes, no. We don't want to run a linear model here. So why is that? Why don't we want to run the linear model here? Yeah, there's this curve and it's not linear looking, exactly. So if you look at these data, we have this curved shape, and look at the range of the data. So the data, we have lots of data kind of down here closer to 0, but the seed weights go up into the thousands, and the seed counts also go up into like the tens of thousands. So we have one point out here past, I guess this is about, somewhere close to 30,000. We have some points with seed counts around 10,000, and then much lower. And so when we have data like this that has this kind of extensive range in the values of X and the values of Y, then this is a scenario where you might want to transform the data. So rather than plotting a linear relationship between X and Y, one thing you can try to do is take the log of both variables, because both variables had like an extreme scale, and first look at the scatter plot for that. So let's go here and use mutate to take the log. So when we do mutate to take a log, what we're saying is we're adding a new variable, log underscore seed underscore count, which is equal to the log of the variable called C count. If we just use the log function with no other arguments to that function, what it's doing is log base E. And so for many of us, we do not use log rules in our day-to-day life. And so you might be like, what does that mean, base E or base 10? Just brush up on the Wikipedia page, maybe watch a Khan Academy video. This is something, and also talk about it in office hours, of course. Something we don't have time to talk about in lecture is brushing up on these log rules, but you need to know a little bit about them for this class. So office hours, the internet, just go to YouTube, be like, what is a log? Math, and someone will teach you, and it'll be great. Okay, so log. We're adding logged variables to our data set. I actually have added them base E, and I've also added them base 10 because there's something I want to show you with them. Now what we're going to do is we've logged both variables. Let's look at the scatter plot for the relationship between the logged variables. So redo the scatter plot, but change what X and Y are. And now look at the relationship between X and Y. And you'll see, using the log base E variables, they're linear. And look at the range between the log of seed count and seed weight. So the seed count variable on the x-axis ranges between like 3 or so and 10, and the seed weight variable ranges between, I guess it goes negative, and 8. So that's the range of these log base E variables. And then if you look at the log base 10, it's the same plot, except the range of the data is different. But you can see that, like, if you just flipped between these two slides, it's like the same, it's kind of capturing the same slope, right? But the intercept would be different because the scale on the y-axis is different. All right, we're gonna work with log base E just because the mathematics are different. There's some kind of like summary rules that we can apply to make our calculations easier. So now we run the linear model on the log data set. And the reason we did that is we plotted the original data. It wasn't linear, so we didn't want to run a linear model. We looked at the data. We saw this large range of both X and Y and thought maybe if we took the log and replotted the data, that it would be linear. So we did that, and it was. So now we're running the linear model using the logged variables. So we pass in the log variable. So this is our Y variable, and the one on the right-hand side of the tilde is our X variable, and we pass in our data set. We call that seed underscore mod for seed model, and then we tidy that seed model to get out our estimates of the intercept and the slope. So the estimate of this intercept is 15.5, and the estimate of the slope is negative 1.52. We can also glance at the seed model, and then we haven't seen this function yet. We can pull the R squared. So remember when we used glance, it produced this small table, and we only looked at the first row, which was titled R squared. There was other rows in that. What pull does, it's a way to just extract the R squared value. Some of you may be thinking, oh, why didn't we use select rather than pull? That's a question for another day. I will just say that they do very similar things, but pull gets you like this number on its own, whereas select would still have the number and call it a data frame. Don't worry about that. Just We used pull, it returns a number. That's all you need to know. Okay, so let's interpret the intercept and the slope estimate. So the intercept, this 15.5, can we see that in our plot? So we can't really see it, right? Like if we were to plot this line, we know that it would hit the axis up here, but we can't really see it. Oh, this is base 10. Let's go to the base E. Right. Okay. So the reason we can't like see it here is because what ggplot does when you plot these data is it kind of cut the range of the axis. So rather than showing you where x becomes 0, it just started the x variable at like 3. And so just imagine that this axis, this x-axis kept going to 0. 0 would be off the edge of my computer screen, right? It'd be way over there. And then you'd extend this line upwards, upwards and to the left, and you'd cross the x-axis, the y-axis, you would cross the y-axis at 15. So that's what this intercept is telling you. If the log of seed count was 0, then the log of seed weight would be 15, which, because we're living in this like land of logs now, it's like, at least to me, very uninterpretable. The slope estimate here, this negative 1.52, what is that saying? For every 1 unit change in the log of seed count, the log of seed weight is going down by negative 1.5. Okay, so as I said, that information by itself, I feel like it's kind of uninterpretable. So how to make it interpretable is to ask a question that looks like this. Okay, so the question could be, what seed count is predicted, or what seed weight is predicted for a seed count of 2,000? So now we're getting back, rather than dealing with laws, we're getting back to the scale of the raw data. And the question is, okay, I have a tree whose seed count is 2,000. Can you tell me approximately, according to this model, how much the seeds will weigh? So what you do is you take your linear model formula, your line of best fit formula, and you plug in what you know. So that formula form was y equals to a plus bx. So here y is the log of seed weight. The a is the estimate of the intercept term from that R output, which was that 15.49. And then the plus bx was the adding the intercept times x. So the intercept is negative 1.52. So you're adding a negative, so you could just have the negative sign, multiplied by your x variable, which is the log of the seed count. So this is our formula. And what we want to do is we're going to input a seed count of 2,000, and we're going to solve for the seed weight. So the next step is to input that seed count of 2,000. So that goes here. And then you keep on solving. So you keep on like just continuing on with the mathematics of this to get that the seed weight is 50.45. To get to this, what we did is we used this property of logs. And this is what I said, like, I don't know. I guess some of you take math classes these days and you remember this, but this is like not stored in my brain anymore. So this is something that you just remind yourself is like a property of logs to allow you to go from here to here. Okay. So this, again, we're not spending too much time talking about this in class. This is something I want you to kind of, let me turn on my lights. I'm not moving enough. Okay, this is something that I want you to like work through on your own and then go to the GSI and say, oh, I didn't quite get that log calculation. Can we go through that? Okay, so, but what this is telling you is that when the seed counts are expected to weigh this 50.45 milligrams for trees having a seed count of 2,000. Okay, so that's like good information to have if you were really into trees. One other thing I want to note was I put milligrams here. And so on the first page of the question, it gave us the units of measurement, and here it was milligrams. So just when you go to write your interpretation of the model, make sure you give me those units of measurement, because otherwise, if you just said 50.45, that could mean grams, that could mean pounds, that could mean a whole bunch of things. So just tell me the unit of measurement, and then you're really interpreting things. Otherwise, like this little thing here is like half a point. Units of measurement, really important. And it makes sense, right? Because if you didn't have this, we wouldn't know the context. And so really important to put those in your interpretation of the question. The other thing, here, yeah, it's just make sure you can do this if you had a calculator, that you can perform this. I wrote calculator just from like when we were working, not remotely, but on midterms and things, you can use R as your calculator. That's fine. So if you want to use an actual hand calculator or know how to use R to do this calculation, either of those is okay. Okay. The last thing we're covering is how do outliers affect the line of best fit. So again, imagine you have a scatter plot and that data is hovered around a line, but you have an outlier away from the line. How does the outlier being present affect the line, affect the slope intercept and the slope estimate and the intercept estimate? So we have another data set that's the spending data, and it's about health expenditure per capita for different countries related to their GDPs of those countries. So we have these data in R for today's class. You can load them in, you can rename some variables, and then you can plot those data. This is what it looks like. So this is health expenditure, and health expenditure here, it's the response. It's responding to the GDP of the country. So the underlying country GDP, health expenditure, I've also labeled the points so you can tell who the outliers are. So you can see there's a really good linear relationship here, but there are two outliers, the US and Luxembourg. So how do having those in the data affect the line of best fit? So what can we do? We can linear model health expenditure as a function of GDP from the data set spending dat. So if we just looked at that, it's going to print out this little window, but I guess what I should have done is I should have assigned this to something and then wrote glance of that assigned object to get the intercept and the slope out of it. But that's what these two numbers are. Okay, then I can add my line of best fit here by using that geom AB line, and I'm going to make it a dashed line just so it's easier to see with these data. So we can clearly see that US and Luxembourg are off of this line of best fit. But what I can do is remove them one by one from the data set and then recalculate my model, re-add my line of best fit. So I can filter those data so that Luxembourg is no longer there, make a new data set without Luxembourg, make a new model on the data without Luxembourg, and then we update our intercept and slope and add that line to the data and make the updated line change its color. So now this is the line without Luxembourg. So the line without Luxembourg, what's going on is that we removed Luxembourg, and what Luxembourg was doing, it was pulling the line towards it. So when we add Luxembourg to the data, the red line becomes that dashed black line. So the red line is pulled towards the Luxembourg outlier. So it really affected like the slope of the line. But we also have this competing force because we have two outliers here. So the US is pulling the line up, Luxembourg is pulling the line down. So how do you affect the dashed line with all the data to be effective when you take the US out? So think about that and then plot it. And what you'll see is that if you took US out of the data, the line would move lower. So it's getting, the line of best fit is pulled towards these influential outliers. And the outliers are data points that lie off of the line of best fit. Had US been an outlier in both the X and Y directions, meaning had the US, rather than its point being at this GDP around 40,000 and health expenditure around 8,000, suppose it was up here kind of on the line of best fit, but outside in both directions, then the line of best fit isn't really affected, right? Because if you remove the US would be already on the line. So removing the US doesn't affect the line. But because the US and Luxembourg are outliers just kind of in one direction, so the US is an outlier in terms of its health expenditure, and Luxembourg is an outlier in terms of its GDP, then they become influential points because they're trying to minimize the distance between them and the line of best fit. And because their distance between themselves and the line of best fit is so far, they have a greater pull on that shape, the slope of the line, than these other countries. So we're going to leave it there. The last two slides are about causal interpretation. So we'll come back to the last two slides on Friday. But that's everything for today. So thanks everybody for coming, and I'll see you on Friday.